This is the second podcast on the topic of visualization in R. We are starting with box plots, strip charts, pie charts, dot charts, bar charts, histograms, a small excursion to 3D point clouds, and a little outlook to animations. Please have the R script ready, such that you can execute the commands that we see in the podcast directly on your PC. Box plots, or first a general remark. The topic of visualization is structured such that you can learn on the basis of examples and illustrations, and also of course with the help of the internet. It's very challenging and also not effective to go into the deep structures of this topic, so best is if you work with examples, download something from the internet and change the parameters to your liking. So that's also how we usually work when we want to visualize something in R. So now box plots can be done very simply. Again, we have the test data function from the previous podcast that generates a data frame with these variables. And we can now just make a box plot of the variable data $size. Small explanation about box plots. We have already discussed that before. So what you see in a box plot is the median, that's the line. Then you see the 75% quantile and the 25% quantile. The definition of the so-called whiskers is different independence of the statistics program you're using or independence of the literature you're consulting. In R, this whisker gives an approximate width of the distribution or some kind of range of the distribution. Eventually it can happen that you see some singular dots on top of the box plot, on top of those whiskers. These are so-called outliers. You can actually split those box plots in terms of factors. So for example, you can look at the variable in terms of genders, meaning you have male and female sizes, and you see that this may be a different distribution. Of course, you can also split it according to several factors. For that, you use the slash. Also here the message is do not overdo it. Then you can adapt the box plots to slightly more complex versions. You can give a notch which shapes the box plot, and there are heuristics telling that if the notches do not overlap, then you have significant differences. So in this case here, you would not really have significant differences between male and female, but this is just heuristics, it's not strict mathematics. You can define the range. The range is the length of the whisker, so use the help in R to see that. That's, as I said before, depending on the definition of your background. You can specify a color for the filling of the box plot. You can choose an alignment, whether they are horizontally or vertically aligned. You can choose the ticks on the y-axis, or you can choose the value or the range of the non-value axis. Non-value axis is here the y-axis. Again, you can of course add a legend. Typically you have to give a position, sometimes a title of the legend. You can specify how far in you want it. You can specify the characters. You can specify the filling color, and you can say whether you would like to have it vertically or horizontally aligned. Here you have a horizontally aligned legend. Again, try it out with the R script corresponding to this chapter and try to change some parameters and see what's happening. So the legend command is exemplified up here. Now we see a first idea of how we can actually use box plots in combination with scatter plots. So what we do here is we have a box plot as a basic of the sizes according to gender. We can color the lines or the surroundings of this box plot with the command border. Then we can say that we, on top of that, plot the data points corresponding to this variable. Be careful, you will have to sort of define an artificial x-axis for these points, such that you have a nice spread over the x-axis of the points. This is maybe not the final idea of how to deal with box plots and overlaid scatter plots. We will come back to that a little later. What is a slightly more advanced idea of combining box plots with scatter plots, but also slightly more complicated, is this one here. So you have a two-dimensional distribution, and you want to visualize the margins, the marginal distributions with those box plots on the side. Here you have to actually play with the parameters of your figure. So this is par fig equal to some vector, and you have to specify new equal to true, right? So this actually specifies the surroundings of your figure. Then you just plot the data, which comes in this case from some randomly generated numbers. And then you add a second figure. Again with some parameters. This is the box plot number 1 for x1, horizontal, so this is this one. Right? With the command figure you have to specify where on the side it should be. Then for the second box plot, again you specify where it should be. Important is the horizontal alignment there, and with x is equal to false, you make sure that you don't have a box around it. So this is a slightly advanced idea. Maybe again play with the code. If ever it becomes useful to you, you may have to adapt it to your needs. So this is maybe also now time to do some short exercises, play around with the parameters in the box plot commands, try to box plot your data or try to box plot some artificially created data to get familiarized with the notions of box plot. We come to the strip chart. The strip chart is a good alternative to a scatter plot if you have clear categories and ideally more than just two. Strip chart, again exemplified with our test data, is following the same syntax as the box plot. Basically you can do all the same, just replace box plot by strip chart. At least for the simple cases. If you want to consider more sophisticated visualizations of points that overlap, then you can choose between stack, overplot or jitter, which is a rather interesting way of showing horizontal properties for data that is actually the same. So this is maybe a little advanced. The code down here produces the figure up there. So you can actually partition this figure into 3 pieces. Now what is very interesting is a combination of box plots and strip charts. I was referring to that already in the box plot chapter. I think this is one of the highly recommended ways of visualizing data that is split into various factors. So you see some kind of properties of the distribution in terms of quantiles, but you also get a chance of assessing the underlying data points here. So this is a very good means of one side simplifying your structure and still leaving justifications or still leaving completeness in your visualization. So how do you do that? It's again our test data set. What you need to do is you just do a strip chart of the data split into the factors you choose. You say that it should be vertical, and you choose a limit of the x-axis such that each factor corresponds to a step of 1. Then you add exactly the same, but just replace strip chart by box plot and put the command add equal to true in addition, and you can specify the borders of these box plots to be red, green, red, green, red, green, right? So that ensures that you separate here by gender. So the females are red, the male are green. So it's also again a good time to practice that yourself. Maybe just take the R script for this section, alter some of the parameters, alter the colors, and if you want to try it yourself, create some artificial data or take data from your own experiments and try whether you manage to visualize them in a combination of strip chart and box plot. The next diagram is the pie chart. We will go here rather quickly because the pie chart is, by the help of R itself, disrecommended. So R is stating that the use of pie chart is not recommended as the human eye is not good at judging relative areas, which you have to do if you want to correctly interpret such a pie chart. The syntax is very simple. You need to have data, you need to have labels, and you just use the command pie. And that's it. If you want to color that a little more appropriately, here's Swiss Politics, then you are also able to specify the colors. We will come back to the idea of specifying colors. There are some color tables in R that specify some, I don't know how many, certainly something like 200-300 different colors. And then you just add to the former command the statement call for color equal to the colors you defined. The dot chart is the next diagram we will have a look at. Honestly speaking, I'm not using this one too often. This is basically a way of, let's say, of visualizing means of some data in terms of factors. But I would say if you have to do that, it's maybe more appropriate to actually use a combination of box plot and scatter plot, or a combination of means and a scatter plot. Because means alone, means of data, or of parts of data, they are not saying anything. Right? You have no idea about the variance, so just plotting some means that is not informative at all. Anyway, here is an example for a dot chart. You can certainly manage to find out yourself what kind of structure you need to provide and what parameters correspond to what functions. We continue with the bar chart, which is another rather famous chart, and however one needs to take a little care about how to publish bar charts. So this is plain vanilla, very easy, just providing data and then typing the command bar plot, and that's what you get. If you want to do it slightly more sophisticatedly, you can add to this data, to this bar plot, a title, labels for x and y axis, and more importantly, names.argument for the single bars. So you can label the single bars in terms of weekdays. You can specify the border of the bars, and you can now even display them in different textures or different shades of gray. What can also be interesting is to stack bars on top of each other. So this gives you an idea of proportions and also gives you an idea of totals. If you would just have one of these bars, you could theoretically use a pie chart. But it's not equivalent because the pie chart is round and therefore more complicated to interpret than the stacked bar plot. The syntax you need to provide is now a matrix. Reasonably, right? Because you need to specify the levels or the heights of the single stacks for each of the columns. The matrix that you provide can look like this. So you have cars, trucks and SUVs. You C-bind that together into a data frame. Maybe you give row names in that data frame. Then it's the data frame, that's the databases. Now, if you want to plot that into such a bar plot, you unfortunately need to provide a matrix, so you have to transfer the data frame into a matrix with the command as matrix. You can specify the different colors and the different densities. You can do this the other way around by transposing the matrix. So that's very same data, just the other way around. Now you split it into weekdays and the stacks are the single car types, vehicle types. You again have a variation in color, the so-called heat colors. This is a special packaging in R that provides colors in terms of a heat map. So this is basically a shading between yellow and red. It can look rather nice, it depends also on the thing you would like to visualize. Of course you can observe here some more. You see that here you have quite some spacing for the legend, it wouldn't fit otherwise. You can do that with the command xpd for expand equal to true, and you set the margins. Margins is the distance to the end of the figure window, so you have a huge distance, this 9 here on the edge. What you can stack, you can also display beside each other. That can be also very useful. Yeah, however, you are not able to estimate the total of a stacked column or a stacked pile, but you see the relations of the single stacks or the single subcategories a little better. This works very easily with the command beside equal to true. Observe that we're using another color set here, it's called rainbow colors. You see that here, color equal rainbow of 5. Just specify how many different categories you have. Here in this case you have 5, and then the rainbow colors will be automatically assigned with the corresponding shading. You can again add a legend, and you see we always do it a little differently. That's for you to see and explore all possible ways of putting legends to a plot. You can also use the bar plots directly with the command tapply, which can become rather handy if you wanna actually visualize mean values. So if you have your data, again with the test data, you just say tapply and say what kind of list you would like to make, and then you already get such a matrix structure. If you just by default bar plot this object M1, say beside equal to true, put some while limit, put some legend, then it looks like that here. You see that if you have a standard legend, you can easily use a built-in legend command here. It's not a separate line. If you, however, have more complex figures, usually the built-in legend commands are not appropriate. Now this idea can be further extended. Here we have a different setting where we have 3 subcategories per factor. And it can even be extended further. So if you're doing a bar plot, then you're visualizing means of your data, and as I said before in the dot chart chapter, means are not informative enough to infer anything on your data, right? Just because the mean number of cars per day is higher 2012 than it is 29, doesn't mean that actually, it doesn't tell you anything because the fluctuations are not clear at all. Right, so if you want to talk about statistically significant differences, you need some kind of error bars. There is unfortunately no pre-implemented function in R for doing that, so we have to do individual coding for this, and there is one. You find it in the library in this chapter. It's called error bars. That library here, and what you need is, or you find in this library, is one single function called error bars. It needs inputs of x, y, upper, and that's it. If you want to specify lower and length, then you can do that, but it's not necessary. X is usually the plot handle. I will show you an example. The y values are those that specify your intervals. It could be a standard deviation. Upper is the length of the upper interval and lower is the length of the lower interval. Sorry, that would be the standard deviation. Here you would have the mean. And length is a plotting parameter which tells you how long this part of an error bar is. If you want to have more details about this function, please ask me. I can explain it, but I think it's not of common interest in this context. Of common interest, however, is what this function does, and it just plots error bars on top of such a bar plot. So when you want to apply it here to our test data again, then make sure that you actually know the means, for example with tapply, and make sure you know the standard deviations. So if you want to show the means, then it's such a matrix here. Now you can just plot those means, and now we have something that we've never done before. We assign a variable name to the plot object. So we say here, for example, BP is equal to that whole bar plot object. So now if I want to put error bars, I need to make sure that the function is loaded. So make sure that you source your library, and then you say error.bars, and the first is the x value, this is BP. The second is the y value, this is this means. And if you want to put standard deviations, then you just put that here, and automatically the upper and lower interval will be defined. Now this is standard deviations. You could also put standard errors, which is the standard deviation divided by the square root of the sample size. I will be talking a little more about that when we will talk about analysis of variance and statistics. What is very worth noting here is that you can also label those bars on top with the command mtext, where you provide all the characters you want to use, all the colors you want to use, and the side where you want to have it. With line equal to -22, you say that you actually move it upwards. At equal to BP is the same thing here as in the error bars. And with the CEX command you say how large you want to have it. So this mtext command can be quite useful. You may have to guess the correct values for this guy here. This is again a detail about the M-text. I've just explained it right now. I won't go through it again, so here you see the details. Be aware that you can also add an additional parameter that is called SRT. We will see that in the end of this podcast. The SRT gives us a rotation angle specified in degrees. So you can make the text appear like that. The next plot is the histogram. The histogram can also be done in plain vanilla style easily by just creating some random data and then doing a histogram of x. The parameter probability tells you that on the y-axis you would like to have probabilities and not absolute values. The command breaks tells you how many bins of the histogram you would like to have. So generally the interpretation of a histogram, in case you have forgotten, a histogram tells you how many times the values in the displayed x intervals occur in the data x. Right, so you can think of these intervals like bins or like drawers into which you put data that actually belongs in. Right, so if you have data that is, let's say, between 0 and 0.3, then it goes into this bin, and the amount of data in this bin is then now 1. If you have another data point falling in, you get 2, and so on. And if you display probabilities on the y-axis, you will not see the number of items in your drawers, but you will see the percentage of these items in a specific drawer in terms of the total number of items you have. So here you have 0. What would it be? Something like maybe 0.2 or 2% of all items in the red bin here. Histograms can be extended, they can be overlapped, they can be shaded, colored, can do a lot of things. You can also overplot some kind of density curve fitting over histogram, unbounded possibilities. In the case here, we have some kind of transparent overplotting, which can be rather nice. We basically just have two histograms with different data, of course. Both have the same y-axis. We specify a density. We specify a color. Now we do that with the RGB color vector. This will be specified more clearly in the appendix, which is a little different between those two. Specify the x-lim and y-lim to be the same. We specify the breaks. And in the second histogram, we have to say add equal to true, such that the histogram is added to the same plot. As already threatened before, one can do more complicated mathematical things. For example, if you have a normal distribution, you can directly plot the Gaussian on top of the histogram. For that, you have to actually know the parameters of the Gaussian. So the command dnorm gives the Gaussian in general. You need to provide a certain mean, a certain standard deviation, which here is 1. And you need to provide a vector x in general. So it's a function depending on x. And then you can just, when you have the histogram done as first, then afterwards you can just say curve and add equal to true, leading to these curves. Now what's very funny here is you can also label those curves directly. That's happening here and here. And for that you use the text command specifying the coordinates, the label, the color, and here also the inclination in terms of an angle. That's an angle of 70 degrees towards the horizontal line. That's almost it. I would recommend you to again look at your script, how far you've gotten so far, and how successful you are with changing parameters and adapting figures to your liking. We will make a small extension towards point clouds here, because that is something that can be rather beautiful. For the point clouds, you need to have the library RGL, which is a standard library in R, so you have to just type install packages RGL. Make sure that when you do this you omit the sign here in front. Then you can create some data, 3 dimensions, right? An X, a Y and a Z component, and then you use the command plot 3D X, Y, Z, color equal to whatever you have. And you can put second data, again with the command add gleich equal to true, color can be red, and then you see this mixture of red and blue colors. What's very nice, please try that out in R, you can actually turn those objects around with your mouse. If you would like to save such objects, then you have to use the command snapshot 3D, and please use the R help to find out what parameters you need to specify. Now we come to a small outlook. So we will treat the for loop in the next lecture. The for loop is a programming concept that can be quite useful for data analysis, data cleaning, data handling. And what's very funny, in combination with visualizations, we can now easily write an animation in R. And I would like to show you this one here. You find this in your script file. So I have here chapter 612 and I execute everything at once, and this is what happens. So we see the letters animation. They are not just turning around, they are also growing larger and they are changing colors. This is a very good exercise concerning the text command and the for loop. So the for loop is something a little complicated. If you hear it the first time, what it actually does is it executes commands in a variety of parameters. Here the parameter is the I, which varies between 1 and 720. What you do is you use the plot command and you just plot nothing. That is with the type equal to n and no axis. Then you put text into the center of this plot. This is at 1, 1. The text should be animation and the angle should be I, so that's first 1 degree and ends with 720 degrees, so that's horizontal. The color is changing in terms of the rainbow color, and the size of the text is changing according to I as well. And since that would go way too fast, if we would just execute this for loop, we need to tell the system that it sleeps for some while between each step. So this is a very nice application. Maybe you can play around with it a little to check whether you manage to rotate it, let's say, the other way around, or change the colors a little bit differently. Now I would like to talk about some 2 or 3 things that do not really deserve to be fully included, but that are here in some kind of appendix. The first thing is a color chart. You see that here you have to turn your head around a little. So here you see all the colors that you can actually access in R with a text. Please check in the internet, there might be even different color charts or even more sophisticated ways of doing that. You can actually visualize that, or those colors that you can display in R with the RGB cube. So RGB is a color model. What you have to specify is the amounts of red, green and blue that you would like to have. That's why RGB, red, green, blue. And you have to define the, opacity or strength of color. and with that you can actually define all possible colors. So maybe you learned once that you can mix all possible colors with combinations of red, green and blue. This is the RGB color model, which can be visualized in 3 dimensions very easily. We just vary those components accordingly, and we see that we have some stuff that is red, green and blue in some corners, and if you compose it and mix it, then you get different colors. You can also use this RGB command directly if you want to color your plots yourself. Maybe it can be useful, but be aware that when you start doing this, it will take some time till you have found the right color combinations. Let me finish with specifying some very typical problems people run into when they work with plotting. If your plot window acts buggy, if it looks weird or something seems wrong, just close the plot window or even type the command def.off and try again. This will erase all previously given graphical parameters that could interfere with your current wishes. What can also happen sometimes are some kind of weird error messages here. For example, in pie chart, it can also happen in bar plot. Some R commands most strangely do not accept data frames as input. They need to have matrices. This is a reason, or this is a mistake number 1 if you have error messages with plot routines and everything looks fine. I am aware that this podcast was a little speedy. We went through a lot of concepts rather quickly. As I said, it is not the intention of this course, it cannot be the objective of this course that you know all those things with a lot of expertise. The idea here is that you have an overview of what you can do with R, and that you ideally practice yourself of filling possible gaps of knowledge in between your desired visualization and your first draft of visualization in R. This topic requires a lot of practice. We will have some case studies for visualization later in this course.